Hey guys, welcome to section 5.2, conservation of momentum and types of collisions. So we've kind of discussed what conservation rules are before. Conservation laws are pretty powerful for us. They do that whole, they're worded, things can neither be created nor destroyed. And so once again, they only apply to closed systems where objects only interact with each other and nothing else. And objects cannot leave or enter the system, and no external forces affect the system. And so we're talking about two particles that will collide, and we're just looking at those two particles and what happens with them. We don't have to worry too much about what happens to the things in the middle of the collisions or momentum conservations, something like that. So just wanted to make sure about that. And then we only require knowledge of the initial and final states of the system. That's a pretty important piece that we need to look at. So we're only looking at the final and initial states. We're taking those snapshots of the system, and those are the things that we're analyzing. So in the last unit, we learned about energy being conserved in a closed system. So like energy, momentum is a conserved property of nature. It's not created nor destroyed. But in an open system, work is done to change the system. Impulse that we learned about, impulse changes the momentum of an open system. So usually we have that external force. That's what that big F meant. Remember, the universe is a big closed system. While momentum or energy can change in an open system, the momentum and energy of the universe remains constant. So that's a very interesting way to think about it. So conservation of momentum, we look at just the snapshots of the before and after. So we see the bowling ball and the pins before, and then after something happens. Obviously the bowling ball will come and hit the pins, and we will be looking at what happens to each pieces of those, and then as a whole as we work through our questions. So we'll recall from our discussion of change of momentum and impulse, we have P sub O, which is momentum initial, and then I is that impulse. If we have an impulse, it will change the momentum of the system. When a net external force acts on an object, it imparts an impulse I to the object, changing its momentum. This is exactly the same for a system of objects. If there's no net external force on the system, the momentum of the system is conserved. So in other words, that's another way of saying if I is 0, the initial momentum of the system is equal to the final momentum of the system. If we wanted to do a big proof, that's too scary. We're skipping that. But Newton's cradle is a great way to illustrate the conservation of momentum. This is obviously an animation, but what's cool about that is that's pretty much how it works. The balls in the middle don't move. We're assuming that all of the momentum of the swinging ball will change the momentum of the ball on the other end. So if just one ball is swinging, it will kick off one ball at the end also. If two are swinging, then 2, 3, so on and so forth. So that's a really interesting idea. So we have types of collisions. So when we talk about momentum and impulse and conservation of momentum, we typically talk about objects interacting with each other, which is basically means they collide. And they can be stuck together, or they can explode or push apart. So disclaimer, an explosion in physics is far less exciting than it is in chemistry. An isolated system, both momentum and total energy are conserved, but the energy can change from one form to another. So I can have some type of potential energy, perhaps in a spring, that can be converted to kinetic energy, and that's those interactions predict what happens, how fast they'll be going, what kind of happens to momentum. So we have basically 3 main types of interactions that we'll look at. We have this thing called an inelastic collision. So two objects will collide, converting some kinetic energy into other forms of energy, such as potential energy, heat, or sound. Typically, those things stick to each other. Elastic collisions, these things bounce off of each other. So kinetic energy is conserved on this one, and energy is not transformed to any other type. So technically, we can't have real elastic collisions, but we estimate them, and so we'll discuss that a little bit in class next. And then we have explosions, where an object breaks apart because potential energy is stored in one or more of the objects and is transformed into kinetic energy. So explosions, elastic and inelastic collisions. So to break this down a little bit further, we have two types of what we call inelastic collisions. A perfect inelastic collisions, the two objects collide and stick together and move as one mass after the collision, transferring some of the kinetic energy into other forms of energy, so heat. Anytime something deforms, technically heat is generated. And then we have these general inelastic collisions. Two objects collide and bounce off of each other, transferring some of the kinetic energy into other forms of energy. So once again, there's really no such thing as a perfectly elastic collision. During all collisions, some kinetic energy, is always transferred into other forms of energy. Some collisions transfer so little energy away from the kinetic energy that can be dealt with as perfect elastic collisions. In chemistry, the collisions between molecules and atoms are modeled as perfectly elastic collisions to derive the ideal gas law. Other examples involve dropping a steel ball bearing on a steel plate, dropping a super bouncy ball onto the ground, and billiard balls bouncing off of each other. The Olympics are this year. If you've watched curling, those are really cool examples of almost elastic, perfectly elastic collisions. And then lastly, explosions. A firecracker is an example of an explosion, of course. The chemical potential energy inside the firecracker is transformed into kinetic energy, light, and sound. A cart with a compressed spring is a pretty good example too. The spring is up against the wall and released. The cart starts moving, converting the elastic potential energy into kinetic energy and sound. So think for a little bit. See if you can come up with an example between this phenomenon and either elastic or inelastic collision. What similarities can you draw there? And so in both an inelastic collision and an explosion, energy changes between kinetic and potential, but they are time reversed. So basically what happens in an inelastic collision, transfer kinetic energy into other forms of energy, such as potential energy, and then explosion, just everything does it backwards. So our problems will be very clearly stated. There's going to be a pre-collision or pre-event situation and then post, and we will be able to figure out, one, if the masses stick together or not, what direction they're going. So once again, momentum is a vector quantity, so which way they're pointing will be really critical in our pre and post sketches of the situation. One of the last things I like to look at is this chart here. So we should have a spot to fill this out. This is a really good way to quantify which one, if momentum is conserved. And notice, momentum is conserved all the time. Momentum is always conserved. There's no reason that we shouldn't get that part right. But if we look at whether kinetic energy is conserved or not, we have either yes or no, and so remembering which type of collision kinetic energy is conserved, and in this case it will be the elastic collisions. In every other collision, kinetic energy is not conserved, and we'll discuss that in a little bit more detail, but think about when things stick to each other, it has to slow down, and so we kind of change how much kinetic energy is in the system at that point. All right, if you have any questions, let me know. Thanks for watching. Catch you later. Bye.